Expect your wave function u to drop to 0, or just go down to 0, as your distance z goes to plus or minus infinity. Right? Now, when z squared, when this, so when z is a large distance, so z is large, so z squared is very large. So when z squared's hugely more, that's what this double arrow means. This means much bigger, not just bigger, but much bigger, hugely bigger than epsilon, eta, alpha, beta, gamma, delta, epsilon. Well, anyway. Eta. I'm going to have to sit down and actually memorize the Greek alphabet. I should know these things. I just never bother. Anyway. Well, whatever this is, what do I call it? Epsilon? Okay, I'll call it epsilon. But I'm not sure it should be epsilon or eta. I mean, they're both e's. Okay. So if z squared is much bigger than epsilon, so therefore you can forget about this 2e here, and so you're just left with d squared u dz minus z squared u is naught, right? Then this here is a solution in the limit. So as z squared becomes much larger than that, your u takes on this form. Now I've asked you homework, show this. So what I'm asking you to do is substitute, put this e to the minus z squared over 2, put that into your equation here. Forget about this, right, because we're assuming z is large, very large, and eventually, if you solve it, I mean, I did it, you'll get like u equals naught. All the other terms cancel out. You just get u is naught, but that's okay because, right? That's assumed. You expect u to be naught as z goes to large values. All right. So here's what your wave function should behave like at large distances, right? So we're guessing now, and a lot of solutions to differential equations involves intelligent, informed guesswork, right? What in English often referred to as a guesstimate, like estimate, but a guess estimate, guesstimate. Now there's a German word for a guesstimate, and it's used a lot in physics and math, and it's called an Ansatz, A-N-S-A-T-Z, and an Ansatz is just a trial function, trial solution that you think probably will work. You're not certain, but it's worth a try, so you put it in. So let's assume that your wave function here, your u, has the following form, that it's some function of z times e to the minus z squared over 2. Right? So this value here, this function is trial function, or trial solution, because we want u. U is the solution to this equation. So our trial solution, if you like, our Ansatz, same thing, just different language, is this, all right? And that's an assumption. Okay, so now plug this, substitute, put this u, put this into this equation, and you will get this, right? So if this is the solution, if it's a u, then if you put this into this equation, you will get this equation, second order differential equation. Now this f of z, part of your Ansatz, part of your trial solution, is that you're half guessing, if you like, that this f of z will be polynomial in form. So sort of like, for example, z to the n plus a constant z to the n minus 1 plus another constant z to the n minus 2 plus another constant z to the n minus 3 ... Okay, so a polynomial, poly many polynomial terms, many terms. Right? Okay, now say the largest power of this polynomial is n, z to the n. That's your highest power. Like if your polynomial was a cubic, it would be like z cubed plus az squared plus bz plus c. Okay. Now, so let's assume your largest power term is to the n, z to the n, right? So if your f is z to the n plus a z to the n minus 1 plus b z to the n minus 2 dot 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 dot, if you put in that polynomial into your f here, then due to this term, the z to the n term, you will get this contribution to the left hand side. You'll get, now if you're differentiating the z to the n twice here, so they'll give you n minus 1, z to the n minus 2, and let's see, where does this come from? You differentiate that once, so that'll give you a z to the n minus 1, but you've got another z, so again you've got z to the n, so minus 2, so minus 2 n z to the n, and the z term here. We're only these are the terms that involve z to the n's. Okay, here. Now, now the whole left-hand side has to equal 0, right? So all the coefficients of the powers of z, so sort of like a z to the n plus b z to the n minus 1 plus c z to the n minus 2 dot 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 dot, all those coefficients a, b, c, they all have to be 0, okay, for the left hand side to be equal to 0. Okay, so what are the coefficients of z to the n? Well, you've got minus 2n here and 2 epsilon minus 1. So add those two coefficients, and that sum has to be 0. Alright, so that means that minus 2n plus 2 epsilon minus 1 must be equal to 0. And therefore, your epsilon here has to be equal to n plus a half. Okay? Your epsilon has to be n plus a half. But what is epsilon? Epsilon is E over h omega. So E, your eigenvalue, is epsilon h bar omega. So I ran out of line. I'm just one line too short, so I just put it down here. So if epsilon is n plus a half, then your allowed energies, your eigenvalues, are n plus a half h bar omega from here. Okay, so we've come to our first major result for the simple harmonic oscillator in the quantum case, that the energies of this vibration of a quantum oscillator, harmonic oscillator, the energies are quantized, right? And the energy values, in other words, the eigenvalues of your ST, these eigenvalues here, are of the form n, that's an integer, and n can be 0, 1, 2, dot, 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 right? So the energies of the oscillator are of the form n plus a half times h bar omega. So at the smallest energy this can have is when n is 0. So then the lowest oscillation energy that your oscillator can have is just half h bar omega, which is not 0. Okay? So there's a kind of lowest energy, a ground state energy that the oscillator can have. Right? Once again, I have run out of board very quickly, so I will stop as usual. Now, I'm curious, a couple of days I will have a board a lot bigger, almost almost double the size. I'll have to calculate. But anyway, a lot bigger. So it will extend the full width of my 3 bookcases. One bookcase, well, here, you can see one just here, right, is that distance is 80 centimeters, and I have three bookcases. You can't see them all, but I have 3 bookcases, so total length of 240 centimeters, and that's the length of the board. And the height of the board, the new one, the third one, is 120, so like half of the length. So I'll be able to put up a lot more on the board, on the new one, in a couple of days. So wait for it.